A electronics project. But before I start with my explanation here, let's go outside to the yard and let me show you what all of this is actually good for. So then, here we are out and about. It's -7 Celsius in my part of the world, and this is my homemade solar tracker, which is already more than 10 years old now, and it works ever since. And its purpose is to charge my 12-volt lead acid batteries, because I have a off-grid system. Let me go closer here. Oh. So it has a slip clutch or storm clutch. That's the reason why I can turn it by hand. Here in this aluminum box here is a geared DC motor, 12-volt DC motor, actually a windshield wiper motor, and the juice goes out through these thick wires here to my battery system. And here inside this box is an Arduino microcontroller, which does the tracking function, which controls the geared motor in the base. Here is a potentiometer to adjust the offset of the thing. So it is a microcontroller based tracking system, and here is the actual sensor. There are 3 LDRs inside this jar here, one facing towards west, one facing towards east, and one facing straight forward. This is for the dusk sensor. So in the evening, when the sun sets, it was already moving. In the evening, when the sun sets, the solar panel has to go back to east, waiting for the next day. And as you see here, I put a strip of aluminium on the jar to cast a shadow on the LDRs. It's a very simple construction. No, I cannot open it, it's frozen. But you get the idea. A jar with 3 LDRs inside, mounted to the solar panel itself, and the solar panels are mounted to a main shaft, which is in itself mounted onto a gearbox. And here is the pivot point to adjust the elevation. I do it 3 times a year. That's enough for such a small system. Yeah, but this is... One moment. This is what the circuit which we will build is good for, to control a solar tracker like this, a single axis solar tracker. Back at the workbench, and here is a analog circuit which does the same thing, controlling a motor for the solar tracker. And it took me longer than anticipated to figure this all out and design the circuit, but there we go, it works and it does the job, same like the Arduino based circuit. Okay, let me explain here. So we have here the main brain of the thing, which consists a quad op amp here, which I will show you in a minute in the circuit diagram. And here is the basic function. The red LEDs show you that both of these sensors are lit. So if I cover one, one LED goes out and vice versa, and the other two LEDs here show when the relay kicks in here of my bird's nest here, the relay shield. So cover one side, and the motor wants to spin in one direction to move the solar panel. In between nothing happens, and if the solar panel is too far off, the motor wants to spin again in the other direction to make the correction. Okay, and also already hooked up to the circuit here is my dusk sensor, which I also will show you in a minute here on the circuit diagram. This lets the solar tracker going back to east when the sun sets. So I cover it up, and yeah, it goes back to east till the solar tracker reaches the limit switch and turns off the motor. Okay, this is the complete circuit diagram of the thing, but as you can already see, it is a very crowded chicken scratch here, and it barely fits on a sheet of paper. That's not very helpful. That's why I will break it down to individual function blocks or sections and explain all the functions here step by step. So let's start with this drawing here. As I said, the main brain of the thing is a operational amplifier, op-amp, a quad op-amp. So this means in this package there are 4 individual op-amps inside. It is the famous LM324N, so a very widely used component. And I used all 4 of these op-amps here in such a way that I used 2 of them as comparators to compare a fixed voltage, namely in this case 2.5 volt, because I'm running the circuit here on 5 volts, to compare the 2.5 volts on the fixed voltage divider here with the voltage divider here with the 2 LDRs, which we have seen before. And I'm doing this 2 times, so everything here inside is more or less complementary built. So one side takes care of the voltage from 0 to 2.5 volt, and the other side here takes care of the voltages from 2.5 to 5 volt. That's why I need all 4 of these op-amps here, because I have 2 motor relays, one for left and one for turning the motor right. Okay, so here are 2 comparators to compare what's going on here, and because the operational amplifier would give out a voltage between 0 and 5 volt, this would also be very helpful. Connected to the output of this comparator here is a Schmitt trigger, also on the left and on the right side, which I can show you here on the other drawing. Let's bring in this one here. Okay, so this is 1/2 of the LM324 here. I have the 2 LDRs, I have a potentiometer to make some fine adjustments to get the offset right. Here is the comparator with the fixed voltage divider and a little bit of feedback here from the output to the inverting input. And the output of this comparator here goes to a Schmitt trigger, which turns on at roughly 3 volts and turns off at 1 volt. So we have a window in between where nothing happens. Also important to note that I don't use the same values. You see it here. On one of the Schmitt triggers I have a 13K feedback resistor, and on the other Schmitt trigger I have a 36K feedback resistor to VCC, because I need a window, so to speak, a do-nothing window. I call it do-nothing window, hysteresis, where nothing happens. So the motor needs some leeway between turning the solar panel to the right or to east or to the left or to west. And I'm achieving this by simply using different values on the feedback resistor here and also here at the non-inverting input here. My dusk switch feeds in and lets the motor spin to east when the sun sets. Okay, so here again I have, here is the comparator circuit, very simple comparator, as I said, a fixed voltage divider on the inverting input and a voltage divider of 2 LDRs in the pot on the non-inverting input. This one feeds in like so to the inverting Schmitt trigger, which, as I said, the trigger low is 1 volt and the trigger high is 3 volt. There is some hysteresis in between. Okay, I hope this was conclusive so far. And coupled to this operational amplifier, here is a relay shield, I call it. Again, we need one PNP and one, can we see this here on camera? We need one PNP and one NPN transistor, because one of these outputs will source and one will sink. And as you see here, we have a limit switch which turns off the relay once the left or the right, or should I say the limit west and the limit east is reached. Just a little normally closed switch here. And here comes the last part of the circuit, which is also crucial, because your solar panel needs to go back to east, waiting for the next morning, and it does this when the sun sets, as I said. And it is a very simple dusk sensor, dusk switch circuit based on a NPN transistor, an LDR, a little bit of filtering here, and a potentiometer to fine adjust the thing. And it pulls, where is it? And it pulls the input here, and it pulls this input here low, like so, if that makes sense. So this took me quite a bit of time to get my head around it and to figure all the values out and yeah, get the function right. As I said, here is the complete circuit, dusk sensor, the LDRs, east and west, the LDR for dusk. Here is my operational amplifier with the voltage divider here, and here, 1-to-1 voltage divider, and this section here is the Schmitt trigger here. And here I have LEDs which show me the state of the thing here, so the red ones which show me how much light is getting to the LDRs, and these two green ones they show me which relay is on, or which output is currently on. And here is my relay H-bridge, very simple H-bridge, the usual stuff here. And here is the DC motor. I added a 5-volt voltage regulator to feed the whole circuit here. It runs on 5 volt, so you can run all this circuit here with voltages somewhere between 6 and 30 volts, depending on what kind of motor you're using on your solar tracker. Okay, here again my circuit, and I soldered up this monstrosity because I had a lot of problems with flaky contacts here on my breadboard, because here an operational amplifier has a very high gain. Okay, so here are my two LDRs again, one facing towards west and one facing towards east. Here is my adjusting pot so that I can make some fine adjustments if it is off a little bit. And notice what happened on the red LEDs. One is gradually fading out and one stays lit, so it shows me which LDR got more light than the other one. And the green ones, they are connected to the Schmitt trigger, so they have some hysteresis where they ignore all the fading here from this LEDs here, and at a certain point the relay kicks in, the motor drives the solar panel, and it turns off. And if the solar panel is off in the other direction, the other relay kicks in, the motor turns the solar panel and turns off the relay. So there is some leeway in between where the solar panel is perfectly aligned with the sun. So that explains this one, the main brain. And here is my not very complex relay shield here on a breadboard. 2 transistors, 2 5-volt relays, some filtering, and there are no motor cables connected now to the relays because it's just for testing purposes here, but both of them work and none of them is on. And here is the circuit, the dusk sensor, again a LDR, 2 resistors, a transistor and a capacitor for extra filtering. And here is another potentiometer where I can fine adjust when in the evening the solar panel turns back to its starting point, so to east. Fine adjust. Yeah. So if I covered it, wait a minute. There's a sheet of paper here. Does it work? Yeah. So if I cover the dusk sensor, meaning it's dark outside, the circuit no longer reacts to these two LDRs and keep spinning until the end switch is reached, and the next morning the cycle can start over again. So yeah, I think now it's time to make all of this into a functional and usable circuit board. This time it will be a single-sided PCB, and the first step is to find the locations for the connectors, screw terminals here, and the relays. The juice comes in here, plus and minus. Here will be the motor connected, motor H-bridge, fuse for the motor, fuse for the rest of the electronics, limit switches, and connectors for the LDRs. Well, let's solder this up. And here comes the usual disclaimer, because I have to say this over and over again. I am not an expert. I am an uneducated hobbyist. I build stuff which works in the end, at least for me. So if you find some design flaws in my drawings or in my finished projects here, feel free to do a better job. What I'm doing here on YouTube is sharing my learning experience with the world. I'm experimenting a lot and I'm enjoying the time hanging out with you here in the shop. And if you want to support me, you can leave a like, subscribe, or even become a Patreon if you want to. If you want to spend $1 or $2, this would be helpful. Finally, after a couple of hours and a lot of swearing, here we are with the final product, the finished circuit board. And I squeezed everything onto this perf board here. It is a wild mix of through-hole components and SMD components. Mainly most of the resistors are SMD resistors here. It's the 1206 package, and also some capacitors here, and the reverse protection here, diode. Other than that, this is exactly the same as you have seen on the monstrosity, this one here, and it works obviously exactly in the same way. Here is my task sensor. Here are the two sensors for east and west. Here are the end or limit switches, which I bridged with wires to test the thing. Linear voltage regulator, 5 volt, a fuse for the circuitry, a fuse for the motor, H-bridge driver, transistors, the offset pot for east and west, the adjusting pot for the task sensor, my red LEDs, my green LEDs, which show me indication which relay is on. Yeah, the H bridge here, the usual stuff. So I would say let's hook it up and give it a try. Fumble, so I hooked it up to my benchtop power supply here, 12 volts. And because I have multiple light sources in here, I also put a torch here on my workbench to simulate natural sunlight here from one light source. And basically all you have to do is to align your sensors here directly to the sun or to the light source and trim the pot to a point where these two red LEDs here, or you can choose any color you want, are illuminated roughly the same, and that's all you have to do. And now if I turn it, one fades away and one relay kicks in, the motor does its thing and goes off again. If I turn it the other way, the motor kicks in, it goes off again. And here is the function of the dusk sensor. Cover the dusk sensor and no more reaction here. So the motor is spinning and spinning and spinning to the point where this contact gets opened, and obviously the motor stops there. And let's have a look at the quiescent current, which could be also a critical point. So when the relays are off, so to speak, when the solar panel is perfectly aligned to the sunlight, we have here 20 milliamp at 12 volts. And let's create an offset to turn on one of the relays here. Now we are talking about 80 milliamps on 12 volt. So still under 100 milliamps. So I would say this circuit is also suitable for very small off-grid systems with a small battery and a small solar panel. Sure. That's fun. So then, since this video is already way too long, I will wrap it up here. And if you found the video somewhat entertaining or interesting, please give me a like, subscribe to my channel, leave me a comment if you want. You can also visit me on the patreon.com/larifari or on the instagram.com/larifariyoutube. I will post the full circuit diagram onto my Pinterest profile as well as onto my Patreon profile. And so far I say follow the sunshine.